the asteroid that struck Earth 66 million years ago, wiping out 3/4 of the planet's plant and animal life, also triggered a worldwide tsunami with mile-high waves. A new study led by University of Michigan scientists reveals that this tsunami scoured the ocean floor and left geologic traces as far away as New Zealand, thousands of miles away from the impact site off what's now Mexico's Yucatan Peninsula. The findings come from the first simulation that models the global effects of the impact of the massive asteroid, named the Chicxulub impactor, upon Earth to reach publication. The team took findings from previous research and modeled the asteroid as an 7-mile wide, 14 kilometers body traveling at 27,000 miles per hour. The researchers supported the computer modeling by investigating the geological record at 100 sites across the globe. In particular, the scientists looked at boundary sections, which are marine sediments laid down just before and just after the Chicxulub impact, and the mass extinction that ended the era of our planet called the Cretaceous period. This investigation supported the predictions the model had made regarding the path and power of the Chicxulub-generated tsunami. This tsunami was strong enough to disturb and erode sediments in ocean basins halfway around the globe, leaving either a gap in the sedimentary records or a jumble of older sediments. Molly Range, who was a graduate student at the University of Michigan when the research was conducted and is the lead author, said in a statement, "The distribution of the erosion and hiatuses that we observed in the uppermost Cretaceous marine sediments is consistent with our model results, which gives us more confidence in the model predictions." Some of the most significant geological evidence found by the team was located 7,500 miles, 12,000 kilometers, away from the Chicxulub crater on the eastern shores of islands to the north and south of New Zealand. Here the scientists found heavily disturbed sediments called allostostromol deposits that were previously believed to be the result of local tectonic activity. Range and her colleagues found, however, that the age and location of these deposits put them directly in the path the team modeled for the Chicxulub-triggered tsunami. "We feel these deposits are recording the effects of the impact tsunami, and this is perhaps the most telling confirmation of the global significance of this event," Range said. The team calculated the initial energy of the impact tsunami, finding that it was as much as 30,000 times greater than the energy of the 2004 tsunami generated by an Indian Ocean earthquake. The event, one of the largest tsunamis in modern history, killed more than 230,000 people. The simulation showed that the Chicxulub-triggered tsunami would have radiated to the east and northeast, into the North Atlantic, and to the southwest, through the Central American Seaway that at the time separated North America and South America, and then into the South Pacific Ocean. Some of the tsunami's most devastating effects occurred deep beneath the ocean's surface, with the team estimating that underwater currents in these and adjacent areas reached speeds as high as around 0.4 miles per hour, 0.6 kph. Other areas such as the South Atlantic, the North Pacific, the Indian Ocean, and the region that is today the Mediterranean were spared the most devastating effects of the tsunami, according to the new simulation. Building a timeline of a prehistoric disaster, the team used a two-stage strategy to model the progress of the asteroid impact and the subsequent tsunami it triggered. The first step was to model the chaos that was the first 10 minutes of the Chicxulub impactor strike, including the formation of the crater and the beginning of the tsunami. This modeling revealed that the impactor hit granite-rich crust covered by thick sediments and shallow water, carving out a crater that was an estimated 60 miles, 100 kilometers wide, while ejecting dense clouds of dust and soot into Earth's atmosphere. Around 2.5 minutes after the strike, the simulation indicates that displaced material would have pushed a wall of water out from the impact site, creating a wave nearly 3 miles high, 5 kilometers, which would have settled down as material began to fall back to Earth. At 10 minutes after impact, tsunami waves nearly a mile tall would have traveled around 140 miles, 220 kilometers, from the impact site, propagating outward in a ring-like shape and sweeping across the oceans in all directions. After 10 minutes, the team's simulation splits into two models that calculated how the giant waves traveled further outward. One of these was the model used by the National Oceanic and Atmospheric Administration, NOAA, to generate tsunami forecasts. The big result here is that two global models with differing formulations gave almost identical results, and the geologic data incomplete. and incomplete sections are consistent with those results. Ted Moore, a paleoceanographer at the University of Michigan, said in the same statement, "The models and the verification data match nicely." From here, the team modeled the further progress of the prehistoric disaster. Within an hour of impact, the tsunami had spread outside the Gulf of Mexico and into the North Atlantic. By 4 hours following the event, the waves had passed through the Central American Seaway and into the Pacific. The simulation showed that 24 hours after the Chicxulub impactor had struck Earth, waves it launched had traveled almost the full extent of the Pacific and Atlantic Oceans and had just entered the Indian Ocean from both sides. 2 days after the impact, tsunami waves had hit most of the world's coastlines. The team didn't estimate how much flooding these tsunami waves would have caused, but they did calculate wave heights in the majorly impacted regions. The simulations indicated that waves in the open ocean of the Gulf of Mexico would have been over 330 feet, 100 meters high. Meanwhile, waves in North Atlantic coastal regions and parts of South America's Pacific coast would have been 10 times smaller, at around 33 feet, 10 m, high. As the tsunami waves approached shorelines in these regions and hit shallow waters, however, they would have soared dramatically in height again. Depending on the geometries of the coast and the advancing waves, most coastal regions would be inundated and eroded to some extent, the authors said. Any historically documented tsunamis pale in comparison with such global impact. Second asteroid. It maybe have been not one, but 2 asteroid strikes that caused the climate change that killed the dinosaurs. It may even have been a cluster of asteroids. The discovery of a new impact crater off the west coast of Africa suggests that the huge asteroid that crashed into the Gulf of Mexico 66 million years ago had a smaller cosmic companion. Scientists already know that an asteroid struck Earth off Mexico's Yucatan Peninsula. The resulting 110 miles wide Chicxulub crater is thought to have caused a decades-long impact winter that killed the dinosaurs. Now, scientists have used seismic measurements to find evidence of an asteroid impact crater, named Nadir, below the North Atlantic Ocean that measures 5 miles and 9 kilometers wide. It's 1,300 feet below the seabed, about 250 miles off the coast of Guinea, West Africa. The simulations suggested the crater was created by a 400-meter asteroid crashing into 500 to 800 meters of water. This would have likely caused a 900-meter-high tsunami, as well as an earthquake with a strength of 6.5. The effects of the newly discovered crater would have been much less than the one that hit present-day Mexico, but it still would have added significantly to local destruction. New discovery makes scientists wonder whether there are other impact craters that they have not yet found. The researchers said they believe the second discovered crater could have formed by the breakup of a parent asteroid. Sean Gulick is a crater impact expert at the University of Texas at Austin. He called the find an exciting discovery that could lead to further investigations of other possible impacts around the same time period. Despite 4 billion years of impactors hitting Earth, only 200 have been discovered, Gulick said in a statement. It is thus exciting news whenever a new potential impact is discovered, especially in the hard-to-explore ocean environment, he added. Other theories. While the asteroid impact theory is the most widely accepted explanation for the extinction of the dinosaurs, there are several other theories that have been proposed over the years. One theory is that volcanic activity played a role in the extinction of the dinosaurs. The Deccan Traps in India are a massive volcanic formation that began erupting around the same time as the dinosaur extinction. The theory is that the volcanic activity released large amounts of sulfur dioxide and other gases into the atmosphere, leading to acid rain and global cooling. This would have had a significant impact on the environment and could have contributed to the extinction of the dinosaurs. Another theory is that gradual climate change played a role in the extinction of the dinosaurs. Over millions of years, the Earth's climate had been gradually cooling, and some scientists believe that this may have contributed to the extinction of the dinosaurs. The cooling climate would have led to changes in vegetation and food sources, which could have had a significant impact on the dinosaurs. Finally, some scientists have suggested that disease or competition with other species may have played a role in the extinction of the dinosaurs. While these theories are less widely accepted than the asteroid impact theory, they are still important to consider when studying the extinction. If you enjoyed this video, please like it and subscribe to the channel. And don't forget to watch the other videos we made for you. Thank you.